First of all, I would like to thank the organizers for this opportunity to share results that were obtained jointly with Natalia Maslova and Alexey Staroletov, as well as to share with you some experience and intuition on problems and solutions related to Gruenberg Kegel graphs. And I'd like to start with the general setup. Suppose that we are given a set of some arithmetical parameters of group. By this I mean something that can be defined with numbers. First thing we require for the set is that it can be easily computed for a large amount of groups in order to study them. This could be like anything. For example, you can take the set of conjugacy class sizes, the number of conjugacy class sizes, set of all elements order, maybe character degrees, character co-degrees, and so on. Second thing we require is that we would like to encode some important group properties by this set of parameters, and that a large amount of groups can be somehow defined using these parameters. And this leads us to, and one of examples of this set is a Gruenberg Kegel graph. Yes, all the groups throughout the talk are considered to be finite, and by POG we denote the set of all prime divisors of the order of a group, and by Gruenberg Kegel graph or the prime graph gamma G of G we mean the simple graph without multiple edges, loops, etc., with vertex set P of G, and vertices P and Q are adjacent if and only if there is an element of order PQ in group G. And in fact, the last dot is equivalent to the following statement. There is an element of order P and an element of order Q such that they commute. So you can decode some information about a group in that way. And there are parameters of this graph that can tell us something about the group itself. And I'll introduce some definitions or representation. By S of G, we denote the number of connected components of a prime graph. T of G, that is the independence number, the maximum number of pairwise non-adjacent vertices of gamma G, or just the maximal size of a co-clique of a graph. TRG is R independence number, that is the maximal number of pairwise non-adjacent vertices of a graph, including the vertex R. And I'd like to show just a little example of how we can obviously compute these numbers. On the slide, you can see the prime graph of the simple exceptional group of type 2E6 over the field with 3 elements. Obviously, there are 2 connected components. The independence number equals 5. For example, you can take a co-clique consisting of vertices 13, 19, 41, 61, and 73. Of course, this co-clique is not unique. For example, you can swap 19 with 37, but you cannot add any vertices without breaking the non-adjacency relation. So this is it. And 2 independence number, for example, we have a co-clique 2, 19, 73, and it is also not unique. And a more complicated examples will be considered a bit later, but to give you some intuition, I provided you an example. So I introduced this notation. Can we, as I said, from the arithmetical parameters, we would like to obtain some group properties to could we do this with these parameters? And if we can, for which classes of groups? And yes, actually we can in some cases, but let me start with an easy observation. Suppose that we are given any nilpotent group. As you may know, every nilpotent group is a direct product of its Syllab subgroups. And if you take any element from Syllab subgroup, it will centralize the other direct multipliers. So as I said, existence of an element of order P such as it centralizes co-prime elements means that vertices P and Q are connected. And it follows that the prime graph on the nilpotent group is connected and complete. So all these parameters are equal to 1. So we can't really tell much about a group about a graph if we are given a nilpotent group. It could be various, as this group could has various structure, and this is it. But maybe maybe situation is different in the world of solvable groups, and actually it is. There is a result by Higman in 1957 that if we are able to find at least 3 non-adjacent vertices, then group is now solvable. So we could just look at a prime graph of a group and instantly tell that it is non-solvable. You have to just find 3 non-adjacent vertices. But in general, the right arrow does not hold from the right to the left, this direction, because you can consider like a direct products of groups, or more precisely, direct power of any group, and the resulting graph will be connected and complete. So with the same considerations as for nilpotent groups. So direct products ruining all in the world of Gruenberg Kegel graphs. By NCV, we denote the number of non-abelian composition factors of G, and the result by Gruenberg Kegel in unpublished manuscript that was published later by Williams in 1981. If the prime graph is disconnected, then there is at most 1 non-abelian composition factor of a group. And a refinement, I'd say, by Vasilyev, 2005. Graph can be connected now. All we seek is just a vertex that is not adjacent with 2. And it will follow that there is at most 1 non-abelian composition factor. And as you can see, prime graphs can really tell us something about the group structure, and we can easily and instantly obtain a lot just looking at a prime graph of a group. But what is the strongest conclusion that can be made on a group by looking at its prime graph? It is the isomorphism type. Is it defined as a group up to isomorphism? And next definitions are pretty standard for recognition problems for like any set of arithmetical parameters. For example, you can change the Gruenberg Kegel graph by any set of arithmetical parameters, and the definitions will remain. Nevertheless, we say that the group G is recognizable by Gruenberg Kegel graph if for every group H, it follows from the equality of the graphs that these groups are isomorphic. Almost recognizable if there are finitely many pairwise non-isomorphic groups with the same Gruenberg Kegel graph as G, and unrecognizable if there are infinitely many pairwise non-isomorphic groups with the same Gruenberg Kegel graph as G. And we'll say that the recognition problem is solved for a group G if we are able to establish one of these points. And actually, I'd like to tell a bit more about almost recognizability. You see, when we established almost recognizability of some group, there's still a lot of work can be done. For example, you can answer the next question: how many groups with the same Gruenberg Kegel graph as G, or give like a list of those groups with the exact isomorphism types. So, and it is very important, but throughout this talk, I will, if group is almost recognizable, that means that our recognition problem for group is solved. Because in most of the cases, we will work with just simple groups, and if group is almost recognizable, in general, it is just some automorphisms of simple groups, and we will see why. Let me remind you that a group G is called simple if it doesn't contain non-trivial proper normal subgroups, and almost simple with a simple so-called S if G lies between S and its automorphism group. And as I said in the beginning, from the set of arithmetical parameters, we would like to the vast class of groups be described in some way. And actually, there is some, if we are considering prime graphs. A recent result by Cameron and Maslova, if group G is almost recognizable, then it's almost simple. So if we want to know what groups are almost recognizable, so solve a recognition problem, for example, in this case, we should go through all the simple groups and their automorphism groups. And of course, there are examples of almost simple groups that are unrecognizable. So the arrow from the right to the left does not hold, but it is the only class we can possibly obtain almost recognizable groups. So it is natural to study it. And therefore, the next problem arises. Let G be an almost simple group. The task is to decide whether the group is recognizable, almost recognizable, or unrecognizable by its Gruenberg Kegel graph. And we will work on this problem. So we know that the only hope to find almost recognizable groups is just simple groups, so it's automorphism groups. But in order to study them, we have to know how they constructed. And actually, we know quite a lot, like everything about them. For every finite non-abelian simple group, we know the number of connected components and the prime divisors that lie in these components. These are works by Williams, 1981, and Kondratiev, 1989. Moreover, there is an adjacency criterion which tells us when whether two vertices are connected or not with an edge. This is the work by Vasily Vdovin, 2005. And using this criterion, we can actually construct any graph for any simple group. And for example, we know the independence number and in general our independence number, but we are mainly focused on two independence number for some reasons, which I'll tell a bit later. And these numbers are presented in handy tables, so it is really useful and easy to work with them. Moreover, as I said, in some cases, it is important to know what cocklix, how cocklix of maximal site are constructed. And Vasily van Dovin, in their work in 2011, showed how they look like, and the results are also can be presented in very handy tables. So if you wanna look for search for some details, you can find corresponding papers. And I'd like to discuss a few more properties of prime graphs of simple groups. The number of connected components lies between 1 and 6. And actually, it equals 6 if and only if L is isomorphic to a sporadic group Yankov 4. And it equals 5 if and only if L is isomorphic to simple exceptional group of the type E8 over the field that is order of which is equivalent to 0 or plus minus 1 modulo 5. But so in general, there are from 1 to 4 connected components of simple groups, and in most of the cases, graph is connected. For any sporadic or exceptional group of Lie type that is not isomorphic to E7, we have the graph is disconnected. If L is a non-abelian simple group that is not alternating, then for every vertex there is some that is not connected to it. In particular, the two independence number is greater than 1. And for every non-abelian simple group, prime graph of which is disconnected, I'm sorry, for every non-abelian simple group, we have either the graph is disconnected or there are at least 3 pairwise non-adjacent vertices, excluding the case when L is isomorphic to alternating group on 10 elements. In that case, graph is connected and the independence number equals 2. And before we move to methods and our results, I would like to introduce one more definition, or rather way of thinking about prime graphs of simple groups. You see, the orders of simple groups are like the product of the field to the sum power and the product of numbers of the form order of field, power of order of field minus 1. And there are works by Zygmundi and Bang that describe the prime divisors of numbers with this form. Therefore, we can use these results to describe the prime divisors of simple groups. And I will not go deeply through the definitions and notation, but I will just introduce the definition of the compact form, excluding some, of course, notation on primitive prime divisors. By compact form, we mean a graph gamma G whose vertices are labeled with marks Ri. And a vertex labeled with Ri represents the clique of the initial graph, or initial prime graph, such that every vertex in this clique labeled by a prime from Ri. And an edge connecting these two vertices in our new graph represents the set of edges of our initial graph that connect each vertex and Ri with each vertex in Rg. Of course, from every prime graph, we can construct easily this compact form, but in general, we do not know how to do the vice versa, because when a field is unknown, we do not really know the exact prime divisors. And just to show you the difference with how we can visualize the prime graph and its compact form, here is just a prime graph for 3D for over the field of order 11. And this is it, compact form. As you can see, we somehow, using Zygmunt theorem, grouped up the vertices. For example, consider a vertex in the compact form labeled by R3. These are vertices in the initial graph 7 and 19, and they form a clique. And from every vertex, there is an edge to R1, that is 5, to R2, that is 2 and 3, and to the characteristics of the field. So as you see, it is easier to visualize the graph using a compact form, but of course, we are able to prove this result without these pictures, but it's just an easy way to think about some graphs and trying to find some properties of them. So now I think it's time to talk a bit about our method and intuition behind this. Suppose that we are given non-abelian simple group, and I recall that we're gonna set task of recognition of simple groups is considered only for almost simple groups. G is a non-solvable group with the same Gruenberg Kegel graph. There is a chain of subgroups, trivial subgroup K, H, and G, where K is the solvable radical, that is a maximal normal solvable subgroup. H quotient by K is isomorphic to S, that is the Sokal simple group. And G quotient by H is just some subgroup of the automorphisms of F. And on the slide, you can see 4 snowmans connected with arrows. And each arrow defines a step of this general method. So so let me tell you first what does the snowman mean. As you can see, there is K below. In the above we have A, that is automorphism, and in the middle we have the Sokal. That is somehow an easy way to decode, to encode information about a group, to easily visualize it. The first step of this method is that we show that S is isomorphic to L. The second step is we proving that the solvable radical is trivial. And in fact, of course, these 2 steps are independent of each other, but I just put it them in that way. If you are able to prove these two steps, then you immediately get the almost recognizability of a group. So I put it AR over the second arrow, because in this case we have that our group G lies between L and its automorphism group. So it's L or some automorphisms of L. And if you want to prove the recognizability of a group, you do the last arrow. You've shown that there are no automorphisms, like proper automorphisms, that have the same Gruenberg Kegel graph as L. And we use this method if we believe that group is almost recognizable. For unrecognizability, this method is not useful, but there is some result that we used to deal with that cases. So, and I will show it a bit later. So this method is only if we believe that group is almost recognizable or recognizable. And before we move into our results, I'd like to give you a bit more intuition on this. In general, if the graph has many components, then it is easier to deal with it. Why? For example, there is a result by Vasilyev that tells us that each vertex in our group, in prime graph of a group that is not adjacent with 2, divides the order of S. And moreover, if we consider any cocklick, there is at most one vertex that divides the order of K or the order of the automorphism group. So all the other vertices in this cocklick divides the order of S. So if the given graph is like sparse, then the structure of our circle is easily to be it is easier to establish the isomorphism types of S in these cases. It is not true in general, but in most of it is not like always works well, but in general it is. And I've heard a lot of talks on recognition of groups by Gruenberg Kegel graphs, but I don't really remember that of course, a lot of results were presented by, I don't remember emphasizing the following. Almost all of the known results on recognizability now are on simple groups or a field of characteristics 2 or 3. That is because of when we know the order of the field, then we can use some number theoretical methods like an easy modular arithmetics or quadratic residues theorems, or more complicated ones like some Diophantine equations, and use all these techniques to get rid of all the different cases. And if we do not know the order of the field, the exact order of the field, it is these techniques, we can just use them, and the structure of the circle is kind of nebulous in these cases. But still present some results that not depend on the field order, and I think these results are the most interesting ones. So considering the recognition of simple exceptional groups of Lie type, all the easy cases, where by easy I mean that we have a lot of components, are handled now. And let me read our main theorem. Every finite exceptional group of Lie type, which is isomorphic to neither Suzuki group nor G2-free, and whose Gruenberg Kegel graph has at least 3 connected components, is almost recognizable by Gruenberg Kegel graph. Moreover, Suzuki groups and G2-free are unrecognizable by Gruenberg Kegel graphs. So let me show you some of the key ingredients of the proof of this result. First of all, one more definition. We say that non-abelian simple group G is quasi-recognizable by the prime graph if for every group H with the same Gruenberg Kegel graph, we have the non-abelian circle F is isomorphic to G. And in fact, it is the first arrow of our general method. And there are lots of results obtained like 10 years ago. First result by Akhlaghi, Khatami, and Khosravi, 2009. 2F4Q is quasi-recognizable by the prime graph. Result by Khosravi and Babai, 2011, that F4Q is quasi-recognizable for even Q. And in fact, when the graph for F4Q has interesting structure, it depends on whether the field order is even or odd. When the field is even, then graph has 3 components, so it's kind of a jackpot. We have definite characteristics, and we have 3 components. And if the order of the field is odd, then there are 2 components, and characteristic can be any prime number except 2. So this is it. And result by Zhang, Shi, and Shen, 2011, G2Q is quasi-recognizable, where Q is an odd power of 3. And to be honest, I don't really know why they didn't prove that the same thing for even power of 3. Of course, some cases, considering some, for example, when circle is isomorphic to E8 or linear groups of small dimension. These are quite hard to handle, but I think it's still manageable. Nevertheless, we prove that G2Q is quasi-recognizable, where Q is an even power of 3. So we obtain quasi-recognition in general case. And in all these cases, we were able to show that the solvable radical is trivial. This is the second arrow of the general method. And therefore, we instantly obtain the almost recognizability of these groups. And we are moving to, I'd say, the most intriguing results. Zvornitsyn in 2013 proves that if G is a finite group such that it has the same Gruenberg Kegel graph as E8Q, where Q is equivalent to 0 or plus minus 1 modulo 5, then G is isomorphic to E8Q for some U that is equivalent to 0 or plus minus 1 modulo 5. And you can ask the following question: why is the difference between the equivalences of the field? You see, when the order of the field is equivalent to 0 plus minus 1 modulo 5, then the prime graph of E8Q has 5 components. And in the remaining cases, it has 4 components. So in some way, it should be harder to deal with this, but still many Zvornitsyn obtained this result, and he used a character theory to prove this also, and he obtained more general results on the fixed points of some simple groups, and we use them in our proofs too. So this is a fascinating paper where this result was presented. However, we were able to show that the same result holds for the remaining cases when the order of the field is equivalent to ±2 modulo 5. And using a few more technical lemmas, it follows that for each value of Q, the group E8Q is almost recognizable by Gruenberg Kegel graph. And why did I say that it is the most intriguing case? You see, in general, when we trying to prove that group is almost recognizable, first of all, we show that it is quasi-recognizable. And this is an example of almost recognizable group, but not necessarily quasi-recognizable group. And it is kind of a rare situation, and this is like a huge series. So it's really interesting. And we are done with almost recognition. And now we move to unrecognizability. As I said, the method I showed you cannot be, we can't use this method to show unrecognizability of groups. But there is result by Cameron and Maslova that for any simple finite group G, the condition of unrecognizability is equivalent to existence of a group H with non-trivial solvable radical such that their prime graphs coincide. And using this result, we prove that if G is Suzuki group or G is isomorphic to G23, then G is unrecognizable. For example, when G is isomorphic to a Suzuki group, there is a result by Guralnik and Tiep. And as Kondratiev told us, it was known to Suzuki that there exists a four-dimensional module V over a field of order of the same order Q, and such that each non-trivial element from each maximal torus of G acts fixed point freely on this module. And it follows that the semi-direct product of this module and the group G doesn't change the group the structure of the prime graph of G. So there is a group with non-trivial solvable radical, therefore it is unrecognizable. So the proof is very straightforward. And the same logic works for G23, but in this case we used also results on Brouwer characters by Jensen. And in fact, we proofs very alike. As I said, all the easy cases are handled now. But what else? Considering, for example, simple exceptional groups. There are 5 more series of simple exceptional groups with unsolved recognition problems. These are G2Q, where Q is equivalent to ±1 modulo 3, F4Q, where Q is odd, 3D4Q, and E6Q and 2E6Q, where Q is greater than 3 because there are some partial results on these groups for the small values of Q. And what should we do in these cases? Like all of these groups, well, all of the prime graphs of these groups has 2 components. So it should be harder to work with them, but still there is hope because the structure of graphs of these groups is like unusual, I'd say. For example, on this slide, you can see the compact form of the graph F4Q. You see there are 2 components, R12 and the components that has the vertex 2. There is an interesting observation. The clique R8 is connected only with 2, and there is no edges with any other primes. So it is a really important observation that can be used to exclude a lot of cases when we are talking about quasi-recognizability of a group FOQ over the odd field. And actually, I would like to present one more result. We proved that groups E6Q and 2E6Q are almost recognizable. So in fact, there are 3 more series of simple exceptional groups with unsolved recognition problem, but we didn't publish this result. We have proofs, but we didn't quite yet ready to get our text done. And why I put almost in braces, because I think that we are able to show the exact cases when these groups are recognizable, and when the automorphisms of E6Q and 2E6Q have the same Gruenberg Kegel graph as these groups. And as you can see, the order of the field is arbitrary. So, and there is really lack of results of this type in the Gruenberg Kegel graphs setup. And going to the end of the talk, I would like to discuss one more problem considering Gruenberg Kegel graphs. First, the definition. The spectrum of a group G is the set of all element orders of a group, and it is also an example of arithmetical parameters. And in fact, it contains a lot more information than Gruenberg Kegel graph. In fact, we can, from a given spectrum, we can build a Gruenberg Kegel graph, but the other direction does not hold. For example, you can consider groups A5 and A6, and actually, a lot of groups are recognizable by the spectrum. In fact, almost all simple groups are almost recognizable by the spectrum. The only unknown things in this situation is when the classical group of rather small dimension, but it is still a prolific theme for research. There is a result by Vasilyev, Vychkaseva, and Mazurov that was actually finally proved by them, but there is still a lot of mathematicians work on this problem, like Shi and others. And if you are interested in details, you can find a corresponding paper. They finally proved the following result. Let G be a finite simple group, and H is a group such that spectrum of these groups coincide. And moreover, we know that the order of G equals the order of H. Then these groups are isomorphic. What if we change the spectrum by the Gruenberg Kegel graph? Are we able to prove the same result in this setup? Actually, no. And there is an easy counterexample. If the order of a field is odd, then graphs for B and Q and C and Q, that is orthogonal groups and symplectic groups, are coincide, and their orders equal. But these groups are obviously not isomorphic. So we can't prove the same beautiful result. But so a problem arises for which simple groups the following is true. If H is a group with the same Gruenberg Kegel graph and the orders are equal, then these groups are isomorphic. And this problem was formulated by Khosravi in his survey paper on Gruenberg Kegel graphs. And I think it was independently formulated by several more mathematicians. So it's kind of natural to study this problem because it was studied, for example, for other sets of arithmetical parameters. And there is a hypothesis on this problem with a star, and I'll explain a bit later what a star means. This problem solves in positive for all simple groups with at least 3 connected components, except for A6, because there is 2 extension of a group A5 that have the same order as A6, but and this conjecture does not hold in this case. And on the slide, you can see all the simple groups with at least 3 connected components, excluding A6. And in fact, the results, we have all the results on this problem, but there is a paper by Khosravi and I don't really remember the co-authors, where they proved quasi-recognizability of groups G2Q, but as we have seen, group G23 is unrecognizable, and a group P cell linear groups of dimension 2 over the field of order 13 have the same graph as G23. So there is no quasi-recognizability, in fact. So modular some revision of these results, and I believe that in general the results, the proofs are correct, and the results are definitely correct. I think that we can state that this problem is solved by this day. So I guess that's all. Thank you for listening. And if you have any question, I would like to answer them.
So, Viktor, thank you so much for your comprehensive talk with many results, with many details. Are there any questions, comments, suggestions? So, if no, maybe I have some maybe stupid questions, but nevertheless, when you obtain some results, for example, about almost recognizability, yes, that some group is almost recognizable, you also obtain, for example, the full list of the groups with the same Gruenberg Kegel graph, but not non-isomorphic groups.
No, we didn't. And we just showed that they are almost recognizable, and of course there could be like any automorphisms that have the same Gruenberg Kegel graphs. And I see that Natalia wanna add something.
Oh, Natasha, please, your question.
I'd like to make a small comment here.
Yeah.
For example, if you consider the case, then you prove the almost recognizability of EHQ by Gruenberg Kegel graph. Then we really have proved that our group EHQ is isomorphic to some EHU for some U, but we do not know all the possibilities for U. Moreover, this is a rather hard number theoretical problem, and at the moment they are working on this problem with specialists in number theory, and there are still no many results. This is really not so easy, and this is not group theory. There are no approaches from group theory to go through this problem. It's just number theory.
Yeah, I understand. Yeah, and so some other questions, comments. So, and maybe one more question. What do you think about the following? Much more groups can be recognized by the Gruenberg Kegel graph and by the order than by only Gruenberg Kegel graph. Or
when we talk about recognition by group K graphs and order, there is a lot more information on group G, so it is natural to expect that more groups are recognizable by the order and the group K graphs instead of just group K graphs. It just contains more information, and like in the recognizability by spectrum, a lot more groups almost recognizable by spectrum than by group K graph, because it just contains a lot more information.
Yeah, but okay, thank you.